Okay. Now, we are defining what? A reaction rate. Reaction rate. Reaction rate. We are saying that the change in the concentration of the concentration of the product or reactant per unit time. Yes. Mathematically, reaction rate being the change in concentration divided by the change in the time. This is for either the reactant or product. Either change in concentration. Yes. Next part of the question. Write down the independent variable. Here we just said that's the type of variable in the investigation where the person performing the experiment changing the variable. The variable that is being changed is the concentration. So your concentration is the independent variable. What about the dependent variable? Time. This is the one that is being measured. A changed by the experimenter, change. This one measured. That's the one that is measured. That's your dependent variable. Dependent variable. That's the one that you measure, and that's the one that changes. Okay, now, what about the control? What must you control here? Okay, yes, we want another two reactants. Yes. The other one has to be kept constant. Meaning, yes, the concentration of the HCl is kept constant. Even from the question, you value the same amount of HCl. You see that? You have to keep the concentration of the HCl constant, because if you change it, it is going to affect the result, your results. So what else can be the control, or must be a control here? The temperature. You don't heat the reaction, because when you heat a reaction, what happens? You are increasing the reaction rate. Okay. Next question. Calculate the value of P in the table. Let's see what you are given there. You are given the volume of the sodium thiosulfate. That it is, for that question there, it is 80 centimeter cubed. Then the volume of water, volume of H2O added to 20 centimeter cubed. It's 20 centimeter cubed. Okay. Now, now, here, we how we are going to do this. We are going to use those values there to find the concentration of the substance, I guess. But in that question, the volume, sodium mole in a 50 centimeter cubed. And the concentration was given as 0.13. What was 0.13? Can you see that? Yes. It's 0.13 mole per decimeter cubed. Now, when you add water, walking at 10 centimeters cubed, about 0.1. Okay. You should be mindful of something here. Something does not change. How to keep it more 50 centimeter cubed? 50 centimeter cubed. And the concentration here is 0.13. From these two values, I can get the number of moles. And the number of moles is not going to change. The number of particles will never change. Where now we change concentration dilute. Can you see that? You should be mindful of that. When you are diluting, their number of moles remains the same. What changes is the concentration. Is that clear? Yes. And this is what we are going to be doing. Number of moles is CV. Can you see that? It's CV, number of moles. So this amount here, which is 50 out of mole to volume. Concentration rating is 0.13 times 50 over 1,000. This value here, whatever it is, remains the same. 0.0. Above guys, 0, give me 1, 2, 0.05. 65, 0.0065, like that. 0, something is wrong. Sorry? So it's 0.0065 what? Mole per decimeter cubed. Per decimeter cubed. Okay. Mole. The number of moles. This is not going to change. That's what we are saying. This is not going to change. Okay. Now, this is how you now get the concentration, how dilute. N1, number of moles you and not Rn, is always going to be constant. C1 V1 is equal to C2 V2, which is equal to C3 V3. No matter how many times you dilute, the number of moles will not change. Is that clear? Yes. So that from here, let's go back. Let's go back here. What we have, we want to find the concentration. Hard to in 80, volume added in 20. Concentration times the volume. Okay. 50. So you are taking only 30 centimeter cubed. And No, but we are keeping this thing here to be 50. Is it 50 so 40, 10, 20. Uh-huh. Okay. So, concentration of this in here. If I hit stage. No. No. Here, I am going to be having this amount. This amount is going to be 30. Mm-hmm. 30. Amount. Then I want to see the concentration. Yeah, thing. If we have this thing here, it is 0,0065. You get what I'm saying? Hmm? The concentration is going to be 30 what? Out of 1,000. Sorry for that. This is out of 1,000 times the concentration. You get that? Then whatever you get from here is going to be the concentration there. Okay? It is 0,21. Like I said, 0,21 mole per decimeter cubed. Per decimeter. Are we all together? Yes. Okay. When 0,21 grams of salt has formed in run 1, the product becomes invisible. Calculate the average reaction rate in grams per centimeter cubed. Nice question. 5.4 there. 5.4. Now, the moment I told you that in chemistry, the moment you are given an amount in grams, we don't work in grams. What do we work with in chemistry? Yes. Convert to moles. You get 1 mark. Number of moles. Number of moles is the amount in grams divided by the molar mass. What is that? It's 0,21 divided by what is the molar mass of sulfur? 32. What does this simplify to? 0, 0. Okay, now, what do we want to, we want to calculate the amount, rather the reaction rate, 0,21 grams of sulfur. Even grams, no, we did not need to convert to moles. Grams per second. Okay. With respect to sodium thiosulfate, but we needed to do that. Okay. The question wants us to do it with respect to sodium. Oh, yeah, we needed to do that. O3 plus 2HCl. Higher with respect to sodium thiosulfate. How much of the thiosulfate was used? Not sulfur. It's not with respect to sulfur. So it was right for us to start with number of moles. Because from the number of moles here, we work out the number of moles by sodium sulfate, then convert to grams. Can we all see that? Yes. So here, the reaction is 2 sodium chloride.
sulfur plus sulfur dioxide. I'm interested in number of moles. Is 1 to 1. Can you see that? What is your conclusion here? Number of moles of sulfur is equal to number of moles of sodium thiosulfate, which is 0,0066. Then convert to grams. Okay. Convert to grams. When you do that, when you convert to grams, how do you do that? King M is equal to number of moles times. Let's do exactly that. Number of moles is 0,0066 times, then the molar mass, let's add, you have 2 sodium. Sodium, guys. From your thing, what is sodium, guys? 23. Plus, then I have 2 sulfurs, 2 times 32, plus 16 minus 4, 64. Add all those, whatever you get is going to be in grams. Sorry? No, oxygen. Oxygen is 16 times 4. How's hydrogen done? Oh, 3. Oh, 48. Sorry. Oh, you mean here? Oh, good 3. Okay, good 3. So this is 48, not 64. 48, not 64. Eva Bukai. 1,04 grams. Now we are going to convert that to grams per second. Now rate in grams per second is going to be 200 grams per second. 1,04 divided by, convert those seconds, give me seconds. Divided by 20,4. Whatever you get here is that rate in grams per second. 0,05 grams per second. Another investigation is performed at different temperatures. Test the Maxwell-Boltzmann distribution curve for the 20 degrees. Label this as A. On the same axis, draw the curve that will obtain at 35 degrees for label B. Now, the general Maxwell-Boltzmann graph is that, again. It is that. Then you have your activation energy here. This, let's call this one here kept A, 20 degrees. Now, on the same axis, this is the number of particles. And this is the energy. Energy here. Then we are going to draw the next one at a higher temperature. Now, at a higher temperature, what you're going to get there is a skewed graph towards the rise. But now, you have to sort of maintain the same number of particles. The area is capital A. Can you see that? That is going to be your graph B at the high temperature. Then you need to know how to translate the graph, Maxwell-Boltzmann graph, for a bigger temperature, a bigger concentration. What else? They are catalysts. Remember the catalyst, you're just going to shift the line, activation energy line, because the catalyst does what? It reduces the activation energy. Then for a higher concentration, you increase, you draw a bigger graph, because the number of particles would have increased with an increase in temperature. Yes. Then explain the effect of temperature on a reaction in terms of the collision theorem. This one here, 5.6. Temperature. The factor here is temperature. We are explaining using the collision theorem. Remember, collision theorem stipulates that all particles constant motion are in constant motion. Again, that for a reaction to happen, there has to be collision of particles. So the first assertion here is that particles must collide for the reaction to occur. What else must happen? These particles must collide with sufficient energy and the right orientation. With sufficient energy. Here, when we talk of sufficient energy, we mean energy that is going to be bigger than the activation energy. Another aspect to this, with the right orientation. The particles must collide with sufficient energy and with the right orientation. Right position of the molecules. Now, when this has happened, all of these, if they all happen, then we call that an effective collision. And that is the one that will result in the formation of a product. But effective collision. Now, based on what we are saying here is, okay, what happens when you increase the temperature? When you increase the temperature, the result is going to be what? At the end, a rise in the reaction rate, an increase in reaction rate. How does this happen? First of all, when you increase the temperature, what happens to the energy? The kinetic energy of the particles increases. That's the effect of increasing temperature. The kinetic energy, increase of temperature. Now, the kinetic energy of particles increases. Then, when there is this increase in kinetic energy, what does that mean? It means that more particles will have sufficient energy. More particles have sufficient energy. This means that you have more particles with effective collision. That's what it means. More particles with effective collisions. When this happens, when you have more particles, then what is the result? The result is an increase in the reaction rate. Is that clear? So when you are explaining in the collision theorem how temperature affects the increase in temperature and reaction rate, pinning point is the kinetic energy of particles will increase. And this does what? It increases the number of effective collisions. If that happens, then you have an increase in. Then the question might be, okay, what about if it's concentration? An increase in concentration. Now, an increase in concentration means what? The number of particles that's what it increases. Not the energy, but the number. The number of particles increases. That's when you increase the concentration, you put in more particles. Then, meaning that more particles will have sufficient energy, meaning that you'll have more effective collisions, and that's how the reaction rate increases. If it's a gas, it's trying to the pressure, not pure pressure. Now, if it's a gas, more highly gas in the pressure. Now, what happens here is we are going to be accurate at the volume here, gas. What is going to be happening here is the volume of the reaction vessel is going to be reduced. Is that clear? That's how you increase pressure. Volume reduced, volume of reaction vessel reduced. That's how you increase the pressure. Meaning that the particles are coming closer together. Can you see that? Particles move closer to each other. And in that way, you are going to have what? More effective collisions. Just from the mere fact that the particles are now close to each other. Then you will have more effective collisions. And if you have more effective collisions, it increases the reaction rate. Can you see that? Then it can again be what? It can be catalyst. If it's a catalyst, what does it do? What does a catalyst do? A catalyst reduces the activation energy, and immediately what happens is more particles will have sufficient energy. And if you have more particles with sufficient energy, then you have more effective collisions. I got it. Yeah. All right. Take note that when you are arguing here, you always want to show how the effective collisions are increased. Yeah. Okay. That was the last question. Now, the last question that we're going to do is question 7. Ethanoic acid. Can we go to that number 7? Yeah, ethanoic acid.
H3COOH is an ingredient of household vinegar. Can we do that one fast? Then go. Yeah.